Welcome to all my viewers to another video session. I hope you've been enjoying my other videos. Thank you for watching, and it's because of you that I make these videos. Right, today I want to touch on another topic, and that is, what is a catalyst? What is a catalyst? So take 30 seconds to think about what a catalyst is, or you can write it down. So basically, a catalyst is any chemical or substance that speeds up the rate of a chemical reaction. So let's say a substance that speeds up the rate of a chemical reaction. Okay, so that's what we refer to as a catalyst. So in general, certain reactions will take forever to occur. All right, so remember, if you have A, SA plus B, chemical A plus chemical B, giving you chemical C. This can take forever, right? So these are the reactants. What we have here are the reactants. We call them the reactants. And what you have here will be the product. The product, okay. So for this same reaction, I can add a chemical or a substance that can speed up this reaction, right? So when I add this substance, usually we do it like this. The catalyst will be written above this arrow. The rate will be faster. Okay. So how does a catalyst speed up the reaction? Okay. For every reaction, you have what you call activation energy. Activation energy. Okay. Now the reactants have to have enough energy within them. Remember, there are electrons that are involved in chemical reaction. So they need to be activated. They need a certain minimum amount of energy, to be able to form a reaction, right? They collide with each other before they can react to form the products. So that minimal amount of energy that you need is what we call deactivation energy, right? So let's write it down. The minimum energy that is needed, or that's the atom or the electrons need to have in order for the reaction to occur. And that's the activation energy. Okay. And I'm going to illustrate this using a simple diagram. So let's get rid of this here. Okay. So let's draw the energy diagram. So I'll put the energy levels here. Okay. So let's assume that to begin with, I have my reactants here at this energy level. So reactants, they need a certain minimum amount of energy. So you have to overcome this energy before they form products. Let's say the product have a higher energy here. So energy of the product. Okay. Let's just extend this line like this, draw an imaginary line here. So this energy that you need, minimum energy that you need, so the product reactants are here, they have to overcome this energy here. So you have to go the way here. It's like pushing them up a hill. So the energy that they need is that is what's called the activation energy. So this is the activation energy from here down there. That's the activation energy. So activation energy. Okay, that's activation energy. So once they have this energy, then the products will form easily, right? So the change in the energy of the reaction is a difference between the energy of the product and the energy of the reactants, and that is here. But we use delta E to represent a change in energy. Okay, change in energy. So your change in energy of any reaction is the energy of the product minus energy of the reactant. That is the activation. That's the change in the energy levels. Okay. So what happens when you put in a catalyst is the fact that the catalyst lowers the activation energy. So catalyst lowers the activation energy of the reaction. Okay. So let's see what's going to happen. I'll use a red color for this. So if we put in a catalyst, instead of the reactant going all the way here, is going to the energy level is going to come down. So it just uses this path like that. Okay. So the reaction is going to proceed along this energy level. Okay. So you've brought the activation energy down, all the way down. Okay. It's all the way down. So it's now here. Okay. So your new activation energy is going to be from here there. That will be your new activation energy. So it's a lower energy level that the molecules have to overcome. Okay. So that's how the catalyst works. So what I've just described over here, this diagram is basically an endothermic reaction. Endothermic reaction. So you have energy absorbed in this case because the energy of the product is higher than the energy of the reactant. So this is an endothermic reaction. So let's write it down. That's an endothermic reaction. So here, energy is absorbed. Okay. So your change in energy, the energy change, which is delta E, is going to be positive. Okay. The products have a higher energy level than the reactants. Okay, good. There's another example where we have energy released. Okay, so energy release. So let's draw this here. If we start with a higher energy level for the reactants, okay, and then the energy of the product is lower. So we have reactants over here, and then product, low energy level. Okay. Now the activation energy is going to be from this point here. This is the starting point for the reactants. So you have to push it up the hill. The molecules have to have that energy. So this is your activation energy here. So this is the activation energy. Activation energy. Okay. Right. And then the change in energy for the reaction will be from this to that. Okay, so this is delta E, that is change in energy, right? So energy of the product minus energy of the reactant. Same over here. Okay, but this time, because the products have a lower energy level than the reactant, the change in energy is going to be a negative number, right? So let's put this down and say that you have a negative energy change, okay? And when that occurs, you have what we call the exothermic reaction, exothermic. Exothermic reaction. Okay. So here we are saying that energy is released. Okay. And then the energy is released in the form of heat. Okay. Exo means giving away. Thermic means heat. Okay. All right. So here we say that delta E, the value will be a negative number because the products have a lower energy than that of the reactants. Okay. So the same way or similarly, if you put a catalyst in this reaction, if you use a catalyst, you will end up with a lower activation energy. So let's show that on the graph. I'll use a different color to show that on the graph. So instead of the molecules gaining energy to get to this peak here, the catalyst will lower the energy level to somewhere around here. So the reaction will just proceed along this path. Okay. So the activation energy will now be from here to there. Okay, now be the activation energy. Okay. So the reaction is going to end up proceeding faster. Right. So with this knowledge, now let's talk about what we call an enzyme. Enzyme. So what is an enzyme? Take 30 seconds to think about what it is. So an enzyme is a biological catalyst. So it is a biological catalyst. Okay. So there are substances that speed up the rate of reactions within a living organism, right? That's why it says a biological catalyst. Okay. So what are some characteristics of enzymes or the properties? One of them is that enzymes are proteins in nature. Enzymes are proteins in nature. So they are proteins. That's one. So because they are proteins in nature, they can easily be denatured or damaged. It can be denatured or damaged. Okay. So they can be damaged by either extreme temperatures or other harsh chemicals. Okay. Now they also act within narrow temperature ranges, right? What we call the optimum, they have optimum temperature range that they work well in. So they have optimum temperature, or let's say optimal temperature range. So they work well within a certain temperature range. The same thing with pH. We have an optimal pH range. Okay. So if you go outside that pH, they will not work well. The same with the temperature. Outside certain temperature range, they will not work well as well. All right. Good. So those are some characteristics of enzymes. And then the other thing I would like to add here is the fact that they remain the same at the end of the reaction. I should have mentioned that also under the catalyst. So catalysts just don't take part in the reaction. They are just there to speed up, all right? So they remain the same, or they remain unchanged at the end of the reaction. So they can be used over and over again, right? So remember that under the catalyst as well. The catalysts don't take part in the reaction. They just speed up the rate of the reaction. They just sit there and speed up the rate of the reaction. So they're unchanged at the end of the reaction. Okay. Right. So these are the characteristics of biological catalysts, which you call the enzymes. Right. So now let's look at a diagram of how the temperature affects enzymes. It's good to know the graph. Okay. But before I talk about that, let me add one more thing, and that is the fact that the enzymes have what we call the active sites. Okay. So we can add it to the characteristics and maybe make point number 6. They have what we call the active sites. Okay. The active sites are the sites or locations where the substrate binds, right? The substrate is what the enzyme works on. So the substrate attaches to the active site of the enzyme. Okay. And one important feature of the enzyme, very important feature of the enzyme, because of the nature of the active sites, they are specific. They show what we call specificity. Okay, so it could show specificity. All right. So enzyme shows specificity. Okay. What do we mean by this? The active sites have a particular orientation. Okay. So only certain substances with the same orientations can bind to that site. You know, it's almost like a lock and key type of mechanism. So if the shape looks like this, then a substrate that has a shape like this that can complement the site will fit in. Okay. Okay. Like a lock and key type of thing. Lock different key. Okay. So for every lock, there's a particular key that can open it, right? So same thing with the enzyme. Okay. Right. So even though the active site is not like the way you have a lock that is fixed, right? It can change the shape. It folds around the substrate. What happens at the enzyme when the substrate binds, the enzyme folds itself around the substrate, it's like embracing the substrate. So if the fit is perfect, then the reaction would occur, right? Yeah. So on that note, let's look at how temperature affects the enzyme. I mentioned the fact that enzymes work in a narrow temperature range, right? So effect of temperature. What is the effect of temperature? And the graph will look like this. If you have the reaction temperature on this side, and let's say that you have reaction rates here. As you increase the temperature, the reaction rate will increase till it gets to a maximum point, and then it begins to drop. Okay. So this is how the graph looks like when you're dealing with effect of temperature. Okay. So this will be the optimal temperature somewhere here. All right. The best temperature somewhere here. The optimal temperature. Okay. So in other words, if you look at the range will be like the enzyme will work well within this temperature range, right? A narrow temperature range, they have maximum activity. So that's how the curve for temperature looks like. Okay. Now the same way, if you think of pH, when we deal with pH, the effect of pH, right? So let's look at the effect of pH. The effect of pH will be very similar. Okay. Same thing. As the pH increases, the activity will increase till it gets to a particular best range. And then it begins to slow down. So over here, you have pH. Okay. So you're going to increase the optimal pH. So this should be pH. And then it will start going down. Okay. So the enzyme works well within a certain range of pH, which will be like this. Okay. So at lower pH, it will not work well. As the pH gets higher and higher, it starts working until it gets to the maximum, and then begins to slow down. Okay. In other words, the higher pH will now start to interfere or with the reaction. It's going to damage the enzyme, just like temperature. Higher temperatures will damage the enzyme. Why? Because they are protein in nature. Protein in nature. Right? Okay, great. One more property that we're going to look at, or one more effect of the substrate on the enzyme. So what's the effect of substrate on the enzyme? The effect of substrate on the enzyme. Okay. So when you draw the graph for this, it's going to look like this. So the gain rate here, and then amount of substrate. Let's put amounts of substrate here. Okay. So when you start adding a substrate to begin with, the reaction begins to increase and increase and increase till it gets a maximum activity rate, and then it slows down. Slow change again. It plateaus off like this. Okay. Right. So what's happening? Now, what's happening is that as you put in, let's say, let me draw the enzyme here. That's active sites. Let's create some active sites. Okay. So let's say these are the active sites. So as you put in, as you increase the substrate, let's make this a substrate. Let's say this is a substrate. So as I increase the number of substrates, more of the active sites will be occupied. So it's going to occupy the active sites. Okay. So the more of the active sites that have been occupied, the greater the rate of the reaction. So it keeps increasing because a lot of the active sites are being bound to. So the rate of the chemical reaction increases. So it gets to maximum. When it gets to maximum, it means that all the active sites have been filled up, right? So the rate slows down, but the reaction slows down because of occupation of all the active sites by the substrate. It slows down, right? So the reaction has to, one substrate has to be broken down and it falls off before another one can bind again, So it's a slow process that is occurring once all the active sites are occupied, right? So it's a quick overview of how the enzyme functions and the properties. Okay. Now we'll be talking about inhibition of enzymes and some other things known as allosteric properties shortly.